.5 operations with matrices. And a matrix is just a way of displaying a group of numbers. We call it an array of numbers. The size of the matrix, we classify rows by columns. RC, like when I was growing up, RC car, like a remote control car. RC, you do rows by columns. So in this first matrix we have here, the rows are the side to side. We have 1, 2, 3, 4, 5 rows by 1, 2, 3 columns. So we would call this a 5 by 3 matrix that tells you the size, sometimes called the order of the matrix, the number of rows by the number of columns. And then if you want to talk about one specific entry in there, we can use subscript notation like this. Entry number subscript 42 means you're in the 4th row and the 2nd column. So if you look down there, 4th row, 1, 2, 3, 4, the 2nd column over would be talking about 16.
What if you have double digits? Like what if there's 10 rows?
There'd have to be a little more spacing down there. Unlikely to have that happen, quite honestly, but you'd have to have like a 10 with a little space and then a number after it, just to make it so you can see it a little clearly. Fair question. All right, so give an example of a square matrix in the space below. A square matrix has the same number of rows as it has columns. So I could say something like 5, 6, 7, -2, 1, 0, 3, 0, 6, something kind of like this. This would be a square matrix. You can have positive numbers in there. You could have negative numbers. You can have 0. You could have fractions. You could have decimals. You could have square roots. All that stuff is irrelevant. But if it is a square matrix, you have the same number of rows, 3, as you have columns, 3. It says, what is the dimension of this one? It would be a 3 by 3 matrix. Question D is a follow-up to this one. It says to circle the main diagonal in your square matrix. So a main diagonal, only in a square matrix, goes from upper left down to lower right. It's going to look something kind of like that. So a little bit of terminology here. Square matrix, same number of rows as columns, and the main diagonal is the one that goes right down the middle from upper left to lower right. Next, what does it mean to have equal matrices? The matrices are equal. We see this little equal sign right here. If they're the exact same size, this is a 2 by 2 matrix, this is a 2 by 2 matrix, and all of the corresponding parts are equal to each other. Specifically, upper left-hand corner, those have to be equal to each other. And we can see from this, yes, -6 is equal to -12/2. Likewise, if these matrices are equal, that means that 4x is equal to 100. And one of the things we're asked to do here is to solve for the variables. So we would say 4x is equal to 100. Do the quick algebra, x equals 25. And that's because these matrices are equal to each other. Those have to be equal to each other, those same spots. I'll go to the lower right just because 9 is equal to 3 squared. Yes, that's true. It should be true. But the other thing we have to solve here is the lower left-hand columns. 15 must be equal to -3y. So divide both sides by -3. And we get that y equals -5. This is what it means to have equal matrices. You set up the corresponding parts to be equal to each other. Arithmetic, matrix arithmetic. First of all, addition. Matrix addition behaves exactly the way you would expect it to. Scalar multiplication behaves exactly the way you would expect it to. So I'm not going to go into some kind of long explanation of this. I'm just going to go into this example right here where it says find b minus 2a. So in order to either add or subtract them, the matrices have to be the same size, and they are. And when you do this b minus 2a, your answer is going to be the same size, 3 rows by 3 columns. And I'm going to help you out with this first row. If you did b minus 2a, looking at the entry that's going to go in this upper left-hand corner, I would have b minus 2 times a. Here's my b matrix. Here's my a matrix. So b minus 2 times a is -9. So what I'm going to have you do is, can you figure out the next entry? B minus 2A should give you a 10. If you got that, I want you to finish off this row. B minus 2A should be negative 4. Once you have this row, see if you can complete the rest of the entries, row 2 and row 3. I'm not spending a lot of time on this matrix addition or subtraction. They're really the same thing. Scalar multiplication, when you multiply all of the numbers on the inside by 2, because I think this is, it behaves the way you would expect it to. There's nothing really weird going on with these. Matrix multiplication, however, gets to be just a little bit more complicated. I shouldn't say it's more complicated, but it's not intuitive as to like what you would do to make this thing work. So what you see in this box is an example of multiplying one matrix by another one. And just like the way you talk about the size of a matrix being row by column, you multiply them row by column. And the other thing you have to be concerned about is not every matrix can multiply by every other kind of matrix. So we have to do a check for that first. So in this example, as I look at this first one, there are 3 rows by 4 columns, which means you're taking a 3 by 4 matrix. So this matrix is 3 by 4, and you're multiplying it by a 4 row by 1 matrix, so 4 by 1. And it is possible to do this. The way that you would know that, and the way you would check, the way you'd find the answer, is that you compare these inside 2 numbers with each other. And since those 2 numbers are the same as each other, the size of your answer is going to be the outside numbers. Kind of looks like a unibrow that works right here, and then you have the smiley face that tells you the size of the answers. You're checking the inside. If they match up, if they're the same, then yes, you can do it. And then these outside numbers are going to tell you the size of the answer. And you'll see that when this matrix was multiplied by that one, we get this 3 row by 1 column matrix, and that's what we'd expect because those are the numbers on the outside. Let me just scroll down here. How do you actually do this? Well, in this next example is a 3 by 2 multiplied by a 2 by 5. You're taking this row by this column. 2 times 0 is 0. -1 times 6 is -6. So then you're adding those together. -6 is what's going to go in the upper left-hand column. You multiply all the numbers in one row by all the numbers in the next column, add all those up, and then that's going to be the number, the element that goes in that spot. Let's take a look on the next page. Rather than spending a lot of time looking at someone else's example, let's go ahead and do our own. Now, a lot of this stuff can be done on the calculator, and we are going to use the calculator for that. I still want you to understand how to do this, especially for the smaller ones, because sometimes you're going to have variables, and you have to understand how they multiply. So in this first example, we have a 2 by 2 matrix, which is being multiplied by another 2 row by 2 column matrix. Check the unibrow first. The inside numbers are the same. That's great, which means they can multiply. Then we're going to take the outside numbers on this smiley face, and those numbers are 2 by 2. So when we multiply the first matrix times the second, we'll get an answer that has 2 rows and 2 columns. Let's figure out the number that's going to go in this upper left-hand spot. So of my answer key, this yellow is in the first row and first column. So we are going to multiply the first row by the first column. 3 times 2 is 6. -1 times 9 is -9. Add those together, and we're going to get a -3. I'll do the other item in the first row. So up here in the upper right, this would be located in the first row, second column. So we're going to multiply the first row by the second column. 3 times -5 is -15. Negative 1 times 7 is negative 7. Add those together, and we get a negative 22 up there. Okay, so I want you to try the bottom row. Can you figure out what goes in the green and what goes in the gray? All right, so there is our matrix answer when we take one matrix times another. So equal matrix, set them equal. Addition or subtraction, just add the corresponding parts. Multiplication, you're doing the RC again, the rows times the column. So letter A, we could have done in the calculator. I don't know if it would have been any quicker because putting all this information into the calculator does take a little bit of time. So doing this one by hand might actually be the preferred method. Letter B is one we couldn't do on the calculator because of those variables that are in there. So let's see, first of all, if it's possible. The first matrix has 1 row by 3 columns. The second matrix, the one we're trying to multiply it by, has 3 rows by 1 column. So here's my check. The inside numbers are the same. The outside numbers tells us the size of the answer. So our matrix is going to have 1 row by 1 column. Now to actually multiply, we take this row times this column, and the number of terms that are in those should match up. So row by column, negative 3 times 2 is negative 6. 2 times x is 2x. And then 5y times 7 is plus 35y. That's just one big entry. Like it doesn't go into separate rows or columns. These aren't different spots. This is the product of this row by that column. Like this number I have right here is like one big term, would be just like one items in those other matrices that we just did. So there's our answer. And this is something you couldn't do on a calculator because x and y are just going to be variables. If you want to read through this, you can. It goes through all the steps of multiplying by using matrices in your calculator. So there is this how-to. We're going to do it in class right now, so you might not need to look at that if you can follow along with what's going on next. We've entered matrices into the calculators before. What I'm going to have you do is go into your calculator and enter this matrix as matrix A. So second, if you can see right above this x to the negative 1, it says matrix. I'm going to scroll to the right and edit. The size of this matrix we're working with is a 3 by 3. And then I'm going to enter in my first row just like it is on my example. So 2, negative 1, 0, 5, 2, negative 5. And then bottom row 4, 0, 3. Once you have that matrix entered in, then you're going to enter in this second one is matrix B. Do that second matrix, you're going to edit. That's when you actually insert the data. Scroll down to B, change it into a 3 by 3 matrix. So we're supposed to take A times B. I didn't even check to see if these can be multiplied. It's not a bad idea to do that. But this one actually does work. We're taking a 3 by 3 matrix times another 3 by 3 matrix. The inside numbers are the same. The outside numbers tell us the size of the answer. So when I multiply these, I'm expecting to get a 3 by 3 matrix. To actually do that on my calculator, I need to go back to matrix again. And this time I'm going to grab letter A. And then on the main screen, it has A with those little matrix brackets around it. Times, go back to matrix again. I'm going to grab name of matrix B. So on my screen, it says A times B. And then it did all of the multiplying, adding, and so forth for me. And the matrix is going to look like that. So letter A, that's what we get when we multiply the first matrix by the second. And you'll notice in the directions it says, note that A and B demonstrate that the commutative property in matrix multiplication is non-existent. Okay, lots of words right there. The commutative property means that order doesn't matter. For just regular addition, it's commutative. 5 plus 3 equals 3 plus 5. Multiplication is commutative. 3 times 5 equals 5 times 3. However, subtraction is not commutative. 5 minus 3 does not equal 3 minus 5. Division is not commutative. 5 divided by 3 does not equal 3 divided by 5. So it's never a foregone conclusion that the commutative property always works. Sometimes order matters. And we're going to see this in letter B. The good news is you've already done all this data entry. This matrix right here is matrix B. And this matrix right here is matrix A. So on your calculator, we're not doing A times B, we're doing matrix B times matrix A. And because it worked one way, sometimes it doesn't mean that the other way is going to work also. So you might not even get an answer, but it's likely that those answers are going to be different. So on my screen, I'm going to do matrix B times matrix A. And you can see that those answers are actually different. So it's nice to have the calculator do all of this for us. It speeds things up a lot. So there's our answer to letter B. So doing matrix multiplication, calculator is a big helper for us. Let's look at letter C before we even go to the calculator, because I don't want to put all this stuff into my calculator if it's not even possible. So in this one, we're going to look at the size of this first matrix. It's 1 row by 2 columns, so that is a 1 by 2 matrix. Times the second matrix has 4 rows by 2 columns. That would make it a 4 by 2 matrix. And my little check the inside numbers, but this is the first time that they're different from each other. So this one is not possible. It can't be done. If you tried to do it, if you tried to take this row by that column, 5 times the 6, 2 times the 1, but then there's this other 1 and 3 in this column that don't have anything to multiply by. That's why it's not going to work. So not possible. Letter D, this one is a 2 by 3 matrix multiplied by a 3 by 1 matrix. Inside numbers are the same. That's great. The outside numbers tell us that when you multiply these, you should be getting 2 rows by 1 column. I'm going to have you try this one on your calculator. The data entry is never very fun, but the more practice you get with that, the more likely you're going to be to remember how to enter this stuff in there, how to find the menus. as I mentioned earlier, if I was going to take a 2 by 2 matrix times another 2 by 2 matrix, I would probably just use my calculator and multiply the numbers. I probably wouldn't input them as matrices because it's probably just going to take longer to do that way. If I know the process of what it means to multiply matrices, take row by column, just using my calculator for the arithmetic is probably going to be faster. Whereas if I get to a matrix 3 by 3, or even like a lopsided one, 2 rows by 3 columns, I'm probably going to use my matrix to multiply just to make sure I'm doing it correctly. So matrices matrices are an array of numbers, a way to display a group of numbers. We can do some things with it. If you can recall back, we've used matrices to solve systems of equations. We use the RREF feature, and we're going to revisit that again in section 7.4. But the other thing we can do with matrices is kind of similar to what you could do like in an Excel spreadsheet, is we can list out all of our numbers and have it do some calculations. Then we can make small modifications to it, which is going to make this a more efficient way of arranging numbers and finding ultimate results. So in this example, 2 tennis teams submit equipment requests to their sponsors. So you have the women's team that want 50 balls, 12 rackets, and 15 shoes. And then there's the men's team that wants 48 balls, 15 rackets, and 18 pairs of shoes. It tells us how much each ball costs, how much each racket costs, and how much each pair of shoes cost. From that, we want to figure out how much each team is going to request to be spent. Now, if this was just all there was, I probably wouldn't use a matrix. I'd probably just multiply what I needed to and get an answer. But after we do this, I'll show you the benefits of using it as a matrix because we might need to change things up a little bit. Don't copy this down yet, but as I look at the numbers that are in here, 50, 12, 15, 48, 15, 18, and if I tried to multiply it by these numbers, say 5, 129, and 79, because I'm thinking I'm supposed to multiply these matrices, would it work in the form that it's in? Could we multiply this 3 by 2 matrix by this 1 by 2 matrix? Not going to work, is it? So I said not to copy it down because I've got the right idea, but I need to change the size of these matrices to make it possible. You notice they both have a 2 in them. This 2 is representative of the fact that there is a women's team and a men's team. Oops, it should be a 1 by 3, sorry. So the 3s are the things that are the same, my fault. So 3 because there are 3 items to purchase, the balls, the rackets, and the shoes. 3 over here because we have a ball, a racket, and a shoes. So we need to figure out a way to change, like flip it. Instead of maybe a tall, narrow rectangle, could you make it in a different way? So from my first trial, which isn't going to work, can you try to figure out a way to multiply these matrices? Once it's set up, then you can go to your calculator, actually multiply them out, see what results you get. And then once we have that, I can talk about like why this is beneficial to do it this way based off maybe some small modifications. It's going to be possible to multiply these matrices. The inside numbers have to match up, and I see that right now those 3s are on the outside. So if I wrote it, the first one as a 2 by 3 matrix, the second one as a 3 by 1 matrix, then the inside numbers are the same, and we get an answer that's 2 by 1. So I'm going to write this, instead of like this, I'm going to have 2 rows and 1 column. My top row, the 50, 12, and 15 is my women's row. The bottom row, the 48, 15, and 18 is my men's row. So first row, second row. And then the other one is supposed to have 3 rows by 1 column. The first row is going to be my shoes, then my racket, and then my balls is first. So balls, racket, and then shoes. And you are able to multiply these matrices. If I do it in my calculator, it will total those up. It'll multiply what needs to be multiplied. As far as the first row goes, it's taking 50 women's balls times 5, 12 women's rackets times 129. It's also taking the 15 shoes times $79 a pair, adding all that up and giving us the total budget for the women. Then it will turn right around and do it for the men. And we're getting $2,983 for the women and $3,597 for the men. So we've got an answer. And again, like, was the matrix really helpful to do this? Could we have done it without the matrix? Absolutely, we could have. But let's say that all of a sudden you're like, the women, you have a budget of $3,600. So you're going to be able to do some more requests. Maybe instead of doing 12 rackets, you're going to try to figure out, what if I change this number to 14? So here's the answer to the question. But go back into your matrix. Can you change this 12 into a 14? So you're just going to the matrix edit. Once you get out of that screen, you can quit and then just go back to your regular screen. If the last thing you did was to take this matrix like E times F or whatever it does, you can just hit enter again, save yourself some keystrokes, and then see how much money are the women spending at this point. And then maybe you say, okay, I'm still under budget. Maybe I can buy a few more things. And maybe for the shoes, instead of spending $79 on a cheaper pair of shoes, I'm going to go for a nicer pair and say, how about I go for the $109 pair of shoes? So I can just go in there and change that one number, and it's going to run all these new calculations based off of making some small changes. It's the same kind of thing that an Excel spreadsheet can do. It's just in a different format. In fact, when Excel spreadsheet does it, it's using like a matrix setup like this in order to do all those calculations. So the benefits of doing this one as a matrix is we can change some of these small data inputs to get some real data for us then. Okay, turn the page. This is your last example, and I'm not going to give you any background information. I'm just going to say, can you interpret this table? Can you make it make sense in order to figure out how much money or the value of the shipments to each of these warehouses is going to be? So it's not an easy thing to do. So can you look at the table, make sense of it, get into the matrix multiplication to find out how much each warehouse is shipping?